You know that frustrating feeling when you try to explain something but it just gets lost in translation? What if we could build a thought so perfectly clear, so precise, that it's impossible to misunderstand? Well, that's exactly what we're going to do today. We're going to build a language of precision from the ground up. Let's dive in. And it all kicks off with this massive question, one that literally powers our entire digital world. How does a computer, a search engine, an AI, anything, actually know if a statement is true? It feels like magic, right? But it's not. It's a formal system of logic, and we are going to build the most important pieces of it right here, right now. All right, so here's the game plan. First up, we're going to figure out how to simply connect the dots. Then, we'll lay down the fundamental rules of truth. After that, we'll learn how to go big and talk about entire groups of things. And finally, we'll put it all together into our very own toolkit for precision. Okay, let's jump into part one, connecting the dots. See, before we can even get into what's true or false, we have to have a rock-solid way to describe how any two things are linked in the first place. The most fundamental way we do that is with something called a relation. And honestly, it's exactly what it sounds like. It's just a big list of connections. Think of it like this. This person goes with this phone number, this product goes with this price. It's literally just a set of pairs that show a connection. But, a simple list can get messy. Sometimes we need something way more reliable, totally predictable. And that's where the function steps in. A function is a special, much stricter kind of relation. It has one critical, non-negotiable rule. Every single input has exactly one output. Zero ambiguity, none. And this comparison here just nails the difference. Look at the relation on the left. It's kind of all over the place, right? One input can go to multiple outputs. It's unpredictable. But now look at the function on the right. It's clean. It's strict. Every input has one and only one path forward. That's the golden rule. Here's the best way to think about it. A function is like a perfect vending machine. You hit the button for Coke, you get a Coke every single time. You press B4 for chips, you get chips. It's completely predictable, no surprises. Okay, and this is the critical distinction, so lean in for this one. It is totally okay for two different buttons, let's say A1 and A2, to both give you a Coke. That's fine. Multiple inputs can point to the same output. What is absolutely not okay is for one button to sometimes give you a Coke and other times give you a Pepsi. That's chaos. That breaks the rule of a function. One input cannot have multiple different outputs. All right, we've got that down. So let's level up. Welcome to part two, the rules of truth. We've nailed down how to formally connect things. Now, let's figure out the rules for connecting ideas and checking if they're actually true. So the most basic building block of all logic is something called a proposition. And all it is a simple statement that is either definitely true or definitely false. For example, the sky is blue. That's a proposition. But what time is it? Nope, that's a question. It can't be true or false. So just like in English, we use words like and or but to connect sentences, logic has its own grammar. We use things called connectives. The big three you need to know are conjunction, which is just a fancy word for and, disjunction, which means or, and the conditional, which is our good old if-then. These are the nuts and bolts we use to build really complex arguments out of simple true or false statements. And this little chart, a truth table, shows you exactly how they operate. Check out the and column. And is really picky. It's only true if both things are true. No exceptions. Now shift your eyes over to the or column. Or is super chill, very inclusive. It's happy and says true as long as just one of the statements is true. Okay, now for the big one, the conditional, the if-then statement. This thing is one of the most powerful tools in all of logic. It's a little tricky because it's not saying P is true or Q is true. What it's doing is making a promise. It's saying, hey, if P is true, then I promise you Q will be true too. It connects a hypothesis to a conclusion. Here's a super simple example. If it is raining, that's our P, then the ground is wet, that's our Q. The whole statement is just a logical promise linking the rain to the wet ground. Pretty straightforward, right? So, the million-dollar question is, when is this promise broken? When is the statement false? There is only one scenario where this happens. It's when the first part is true, it is raining, but the second part is false. The ground is somehow bone dry. That's a broken promise. That's a lie. So the whole if-then statement becomes false. In every other situation, the promise is technically not broken, so the statement is considered true. Okay, deep breath. We're moving on to part 3, all versus some. So far, we've been dealing with single statements. But what if we want to make a big claim about an entire group of things? This is where we learn to scale up our thinking. To do that, we need a new tool called a predicate. The easiest way to think of a predicate is as a proposition with a fill-in-the-blank. So a statement like, X is an even number isn't true or false yet, right? It's just waiting. But the second we plug in a value for X, say we plug in 4, boom, it becomes a true proposition. If we plug in 5, it becomes a false one. Now, here's where it gets really powerful. We take that predicate and we combine it with something called a quantifier. There are 2 main flavors. The first is the universal quantifier. It looks like an upside-down A, and it means for all or for every. This makes a huge, sweeping claim about every single thing in a group. The other is the existential quantifier, that backwards E, which means there exists or for some. This one makes a much humbler claim, just that there's at least one. And as you can imagine, the burden of proof for these two is wildly different. To prove a for all statement is true, you have to be right 100% of the time. You find one counterexample and your whole claim collapses. But to prove a there exists statement, all you got to do is find one. Just one single example that works, and you're done. You've won the argument. What's really cool is how these two are opposites. Let's say I make the claim all birds can fly. To prove me wrong, what do you have to do? You don't have to prove that no birds can fly. You just have to find me some bird that cannot fly. You just have to point to one penguin. So the negation of for all P of X is there exists an X that is not P of X. The opposite of all isn't none, it's some are not. All right, let's bring it all home. Let's wrap this up and look at the amazing toolkit for precision that we've just built together. We've basically assembled a powerhouse system for thinking with absolute clarity. So think about what we did. First, we laid the foundation by defining connections with relations and functions. Then, we built the walls of our arguments using propositions and connectives. And finally, we put the roof on by learning how to make these big, general claims with predicates and quantifiers. You see how each piece stacks perfectly on top of the last? So, why should you care about any of this? Because this isn't just some abstract math puzzle. This is, and I mean this literally, the code of a thought. This is the fundamental logic that powers everything from computer programming to database queries to the very way that AI systems reason. It is the blueprint for how a machine, and for that matter, a human, can think with perfect, undeniable clarity. So I'm going to leave you with a final thought, a challenge. We've just handed you a toolkit for building precise, unambiguous thoughts. So my question to you is, what's one idea, from your job, from a hobby, from anywhere, that you can now go and explain with perfect precision?